Okay, so in this video I will give you some basic overview of the fundamental concepts of hydraulics, which is required by the mechanical and civil engineering students in the first year integrated engineering course at UCL. And this is relevant to the global health challenge of this course. So your challenge requires you to find out how you can design a system to produce energy out of a flowing water stream, right? Because that's how hydroelectricity or hydroelectric power plants work. So how do you go about addressing that question? Well, what you do is you make use of a concept of what is called total head, or which is one way of analyzing total energy at a point in a flowing fluid stream or a water stream in your case. And what this is basically energy per unit weight at any point in a flowing fluid stream. Okay, so what you see here are the different components of energy that add up to give you the total head or the total energy at a point in a fluid stream. So what are the different components of the total head or total energy? Well, the first part is pressure head, which is denoted by P pressure divided by rho g. Rho is the density of your fluid and g is acceleration due to gravity. So this is referred as pressure head or pressure energy. The second component is kinetic head or kinetic energy, which is velocity v squared divided by 2z. And the last part, represented by symbol Z, is the potential head, where Z is position of the point that we are talking about, where you're trying to calculate the energy, the position of that point with respect to any reference frame. Now you'll notice that the terms in this expression, the terms in these expressions here, the different terms here, they have dimension of length. I mean, it's very obvious that this Z here is position of a point with respect to a reference, so that has got to be a length unit, right? So if you do the dimensional analysis of all the different terms here, you will actually come to the dimensions of each of these terms as length with the unit of meter, right, in SI unit. Now you may think that this is fairly weird way of calculating energy. I mean, it doesn't seem like energy at all. Where is joule or where is watt for power, for instance? Well, the reason we make use of this concept of head is this is a nice way to analyze energy per unit weight of the fluid. So if you take this head and you multiply with the weight of your liquid, you will get the total energy. So if you think about it, your objective in the challenge is going to be something like producing, let's say, 10 kilowatt of power or 50 kilowatt of power. So how do you go about doing that? Well, you calculate the amount of energy available to you in terms of head, the total head available to you. Let's say that is 5 meters. And you can multiply that 5 meter of head with a certain amount of flow rate in order to get to the 10 kilowatt or 50 kilowatt of power that you are going to generate, right? So it helps you calculate the required amount of water flow rate that you need in order to obtain a certain amount of energy. Make sense? Okay. So your second aspect of your challenge is to calculate the amount of water flow rate. And so you can tell that both of these are essentially related to one another. So how do you go about making use of these expression of total head to actually calculate the amount of energy that you can generate and the amount of water flow rate that you can have out of a system? Okay. So the first bit is to think about how much energy is available to you in a hydraulic system or a system where water is flowing. That's what hydraulic systems are, right? So in the right here, I'm showing you a schematic which is not very different from the kind of structures that you will be analyzing. So what I have is a reservoir here which has water at a certain level, AHR, and I'm connecting it to a series of tubing so that this tubing can be used to drain water out of this reservoir at this point 2. Now obviously the water in the reservoir is at a certain height above the point 2, so the water has a lot of potential energy associated with it, right? So if I start to drain water out of this tubing, the water will come out at a certain velocity here. It will come out with certain amount of kinetic energy, right? And I can make use of that kinetic energy to produce hydroelectricity. How can I do that? Well, by using turbines, of course. So this schematic is not very different from the kind of system that you would like to analyze, right? You can replace this reservoir with a river, for instance. It doesn't change the thing, or your analysis. The basic analysis remains the same. Now the symbol Q here represents the volume flow rate. Okay, keep that in mind. So let's think about how much energy is available to us at point 2, which we can make use of in order to generate electricity. Okay, because that will sort out the first bit that we need to analyze in this challenge, right? Okay, so we can do that by using this expression here. So let's start with point 1. So at point 1, I have a total head or total energy of H total 1. How much of that will make down to the point 2 here? Well, H total 1 minus whatever head loss that I will encounter as my water starts to flow through this piping network, because we are analyzing a realistic system, so you would expect certain amount of losses, and we represent that in the form of head loss, H loss. So if I subtract the losses from the total head or total energy I've got available at point 1, I can obtain the energy at point 2, right? So that's the energy available to you in order to convert into electricity, right? Okay, what about the flow rate? Well, if you could calculate by your analysis, let's say the velocity at this point, okay, out of this pipe, you can immediately find out what the flow rate is, because flow rate in a flow stream is nothing but velocity times the area of cross section of the piping, or the area of cross section of the flow stream. So what is the area of cross section of this, let's say, circular pipe here? It's nothing but pi times dp square divided by 4, where dp is the diameter of the pipe, times the velocity here. So if you could figure out the velocity at this point, you will not only know the kinetic energy that is coming out, which you can convert into hydroelectricity, you can also find out the flow rate, right? And you can multiply the flow rate with a certain amount of time in order to get the total amount of water. If you want to calculate or if you want to find out how much water needs to be delivered to your vaccine plant, and if you know that number, well, by multiplying this flow rate with a certain amount of time, you can calculate how much time you need to give your system in order to obtain the amount of water down below here, right? And the next thing that you must think about is, well, if you're delivering water, the water has to be delivered in a steady form. I mean, if the water flow rate here starts to vary too much, that's not going to be good, is it? So in your design, you should think about, or you need to think about, how do you design or select this piping diameter or the diameter of the reservoir and things of that nature in order to have as uniform a flow rate here as possible, right? Okay, so let's come to the analysis bit here and start by calculating and see how we can calculate the velocity at our point 2 here, right? So what do? Well, we go back to our original head equation. So I start with my total head at point 1, which is nothing but P1 by rho g plus V1 square by 2g plus Z1 equals the head on the right hand side, which is the head at point 2, plus any losses that I'm going to encounter as the water flows from my reservoir to my outlet, right? Okay, so let's think about losses now. What are the different losses you can have? Well, you are analyzing a real system, right? So water is a fluid which has certain amount of viscosity associated with it, and due to this viscosity, as water flow through your pipe, it will suffer some amount of viscous losses, which are also called frictional losses, okay? And that's shown here. And the way you you express viscous losses, or any loss for that matter, any head loss for that matter, is by using a constant which is called a loss coefficient. So for your frictional loss, HF, you have the corresponding loss coefficient times the velocity head. Now what is this velocity head? Which velocity are you going to use? Well, if the liquid is flowing through my pipe here, it's the velocity of flow here in the pipe. Okay, so for instance, if my flow velocity here is V2, and if my pipe is uniform in diameter all the way from up here to down here, the velocity is not going to change, and so this is going to be the velocity V2 itself, which I'm after. Okay, what are other losses that you can have? Anytime a liquid has to go through a change in cross section, so you can already see the reservoir here is fairly big, and the liquid has to make itself from the reservoir into this little tubing, so it is undergoing a change in cross section. That causes losses. Anytime fluid has to undergo any bends, that causes losses. If the fluid has to flow through any valve, or if it passes through any fittings, all of these bits lead to certain amount of losses. Now how do you account for those losses? Well, each of these losses are going to have a constant K associated with them. Okay, so if you are after calculating the total loss as the liquid flows through your system, you must add up all the different loss constants. So you must add up all the different losses. So your total loss essentially is going to be K1, which is loss 1. Let's say that's the viscous loss. K2, which may be due to this bend here. K3, which may be due to another bend here. K4 due to another bend here, and so on and so forth. And you can add all of those up, multiply with the velocity head, the corresponding velocity head, in order to get the total loss. Okay, so one of your homework here for today's lecture, before you come to the next workshop, is to read the fluids note that I have posted on Moodle under the MECG tab. You need to research the different loss coefficients, okay, what they are. You will find basic idea about those in the fluid note itself, and I'd like you to figure out the loss constant for different piping diameter, piping material, and so on and so forth, because you will actually be designing this kind of a system. So you will not have luxury of just taking any random loss coefficient. You will need to figure out the value of these different loss coefficients. In particular, the loss coefficient or loss constant for the frictional losses needs to be determined by a two-step procedure, which you will also find if you read this note here. Okay, so how do you make use of these equations that you have learned? Let's say we have looked at so far. Well, this is what we have, right? This is the original energy balance equation or head balance equation. These are the total losses. For simplicity, you can represent the sum of all these loss coefficient as a constant K, which you will determine through your research, times the velocity head, right? So obviously we need to make some simplification if we want to find out what the velocity at point 2 is. The first simplification that you can make is, if you think about it, the cross-sectional area of your reservoir here is much larger than the cross-sectional area of this pipe. So for the same flow rate, right, the velocity here can be very small compared to the velocity here, right? The rate at which the level here will go down will be much smaller than the rate at which the flow will come out here. Okay, and that's basically what we refer to as a continuity equation. Now I will encourage the civil engineering students among you to talk to your mechanical engineering colleagues, because they have had the basic discussion on continuity and energy balance in their introduction to mechanical engineering course. So you need to discuss this among each other in order to convince yourself that the velocity at point 1 is going to be a lot lower than the velocity at point 2. So you can make an engineering judgment. You can say that I can disregard the velocity head at point 1 because the velocity at point 1 is very, very small. What else you can do? Well, if you look at this reservoir is open to atmosphere. So the pressure here is equal to the atmospheric pressure. What about the pressure at point 2? Well, again, the flow as it comes out becomes exposed to the atmosphere. So the pressure here is also atmospheric pressure. Now if you go back to this equation, the pressure P1 and P2 are on the opposite side of your equation and they are both equal to atmospheric pressure. So you can actually cancel those two guys out. So we have now substantially simplified the equations, and let's now collect the terms. So what do we have? We have Z1 on the left hand side, Z2 can be brought to the left hand side with a negative sign, and on the right hand side I have the velocity head square plus the head loss. Well, let's see how we can further simplify these things. So the first thing to note is what is Z1 minus Z2? Well, Z1 is the height of point 1 with respect to your reference. Z2 is the height of point 2 with respect to your reference. So it's basically the height difference between point 1 and point 2. And what is that? That's nothing but HR plus HP. What is HR? HR is the height of water level in the reservoir, and HP is the height of the reservoir base with respect to point 2. So Z1 minus Z2 is HR plus HP. V2 squared by 2G remains. You can substitute for H loss in terms of K times V2 squared by 2G. That's here. You can of course take out V2 squared by 2G as common. So you get 1 plus K times V2 squared by 2G. So now from this equation you can calculate what V2 is, and that's what's written here, right? So this gives you a way to calculate the velocity at point 2. If you think about it, everything in here is known to you. G is a constant which you can which is 9.81 meters per second, meter per second square, right? Then K is a constant that you will determine through your research. HP you can measure for your reservoir system. HR is the water level in the reservoir, which you can also measure. So you can find out the velocity, right? If you have the velocity, you can go back to your previous equation that we saw a few slides back to calculate the flow rate at point 2. The flow rate with which the water is coming out of your pipe at point 2, right? Now, there is one subtle aspect here that you need to keep in mind, and that is whether this flow rate is constant or not, right? We were talking about it earlier. So if you think about it, the water level in the reservoir is going to change with time. Why? Well, you are draining the reservoir, so the water level is going to decrease with time, right? Now look at this equation here. This has the water level or the height of the water in the reservoir, right? So if this thing is decreasing with time, your V2 is going to change with time. If V2, the velocity at point 2, is changing with time, this equation tells you that the flow rate here is also going to change with time. So you need to keep this in mind when you are designing your system.